before we start, or anything that you want me to focus more for the coming exam? Actually, you feel not quite comfortable with that concepts or kind of questions you have, you can ask now actually. From Justin, let me see. Can you go over an example of a conditional convergence? Sure. Before we start, let me answer some of the questions. It's very important that you ask questions, so that this is definitely to help you guys. So an example of conditional convergence. Okay. Actually, there are abundant examples which is conditionally convergent, because let's look at the most typical one, the series given by the P series. Okay, so if we look at the series like this, n goes from 1 to infinity, we know that this series will be convergent only one P is larger than 1, right? So that's something we know. So this is a positive series, meaning every atom, every term in the series is actually always positive, larger than 0. So this is a positive series. And for that reason, this one is, and we know from the P series test that this will be convergent only when P is larger than 1, sorry. How can we modify this so that every atom in the list, when P is larger than 0, is always convergent? We can look at the following example. This will be convergent when actually P is larger than 0. So the extra thing we gain by adding this sign here is that now for P larger than 0 and smaller and equal to 1, it is always convergent. So let's look at one example here. Let's look at the following example. This is the case where P equals to 1/2, right? Which is smaller equals to 1 and larger than 0. If we don't have the sign here, if we don't have this part, this as a P series will be divergent. But now when you add this -1 to the nth power, this new series now is convergent by the alternating series test, because the nth term decreases to 0, right? That's something that you can see. So this is a typical example of something which is not absolutely convergent, because if you take the absolute value of the series, you get the P series, which is divergent. But as a series itself, it's convergent by the alternating series test. Convergent by the alternating series test. But App's value is divergent, right? So this is a very typical example of something which is convergent on its own, but when you take the absolute value, you get something that's divergent. Does this answer your question, Justin? Okay, perfect. So do you want me to give you another example? Because I think this is a very typical one. So one thing I want you guys to understand is the following theorem. If summation sigma an, n goes from 1 to infinity, is convergent, then summation n goes from 1 to infinity an is convergent. What's the meaning of this theorem here is that if this series, F's value of the series, is convergent, meaning every atom is positive, when you add a bunch of positive things, it's convergent. Then if we allow something to be negative and something to be positive, this original series will definitely be convergent. So this is a point why if the F's value of something is convergent, we call it absolute convergence, because if the absolute value of the series is convergent, that automatically means the original series is convergent. So that's the reason why we name it absolute convergence. meaning it's a stronger condition on convergence. But conditional convergence just means itself is convergent, but when you look at the positive terms, it's not convergent. Okay. Any other questions?
I have a question I had trouble with on the WebAssign last night.
So let me make my video audio larger sound. So what's your question?
So there's two. One you went over last week, but I couldn't recreate it. I guess you skipped a step or two on my notes, but it's the sum. So there's two questions. One of them is the sum from 1 to infinity of n factorial x to the n over n to the n.
N factorial to the what?
X to the times x to the n all over n to the n.
N to the n. Okay. To find the interval convergence, you mean? Yeah. Okay. And you said there's another question?
The other question is the sum from 1 to infinity of 2x to the n plus 1 over 8 to the n plus 1 over 8 to the n plus 1 times n to the 8.
8 to the n plus 1 times
n to the 8.
N to the 8. Okay.
And we're supposed to find the radius of convergent for each.
Okay, so let's do these two questions. And let me do the one on the left-hand side first.
Thanks, Bo.
This is very important, actually. You know how to find the radius convergence and also the interval convergence for these kind of questions. This will, for sure, be on the final exam. That's a must. So you should definitely review these and understand everything. So the way I always do this is I first let an to be everything involving x to the nth power. So an is n factorial to the n x to the n, and also n to the nth term. So then what is an plus 1? Let me, before we actually jumped into the ratio, let me write down explicitly what an plus 1 is. So an plus 1 in this case equals to n plus 1 factorial times x to the n plus 1 in this case. And also for the numerator, for the denominator, we have to be careful because there are two n here involved, the one in the bracket and the one that's in the exponent. Okay. So there we know that limit, actually, yeah, let me write in one sentence here. So we are interested in the limit of the absolute value of an plus 1 over an for the sequence I just defined involving x. This actually equals to, so let me use a larger sentence here. It's n plus 1. Sorry, let me actually do this. N to the nth power. There's no n plus 1 here. Okay. And we have the n plus 1 factorial. We have the x to the n plus 1. And in the denominator, we have n plus 1 plus to the n plus 1 times n factorial times x to the n. Do you guys agree that we have all the terms matched up? So in each of the atom here, you see there are three distinct parts, the n factorial parts, the x to the nth part, and the n to the nth part. So in your ratio, there should be three parts dividing each other, right, correspondingly. Okay, so this is what you get when you write down the ratio correctly. And then the next thing is to do the algebra. Okay, but you see that n to the nth power, let me write one more step before I jump into the cancellation, is I want to have the denominator, this term, to have to the nth power, n plus 1 to the nth power. If I write like this, that means I have an extra copy of n plus 1 left over. And I also have n plus n factorial, and I have x to the nth power. Now everything's clear, because now I can do some cancellations. The n plus 1 factorial divided by n factorial is n plus 1. Do you agree? And you have an extra copy of n plus 1, so everything here divides each other, cancel each other. Okay. And what's left over is n to the nth power and n plus 1 to the nth power. So that gives me n over n plus 1 to the nth power times x. Is that right? Okay.
Yep.
So a different way to write this, let me actually write in a way that's more familiar to you guys, is the following way. Is x divided by 1 over n to the nth power. So basically what I'm doing is, rather than writing this as a product, I write them as a quotient. So henceforth, I have to take the reciprocal of everything in the fraction here. And that becomes 1 plus 1 over n. Okay? So can someone tell me what's the limit of this expression here? What's the limit of 1 plus 1 over n to the nth power when n goes to infinity? Anyone who wants to give help me a little bit here?
Is it e to the negative 1?
E to the negative 1, oh, x to the n over e.
Right.
So you want this to be smaller than 1, right?
Can you go through? I mean, I know maybe it's kind of takes a little bit longer, but the 1 plus 1 over n to the n. I know it's stuff we've been doing in chapter 7, right?
Uh-huh.
Can you just do it very quickly?
You mean find the limit of that?
Yeah, with you bring it out front and flip it. I guess it's not that bad. I was having trouble with it last night. Never mind.
Yeah, this example should be, I mean, if you're talking about finding the limit of this expression, the 1 plus 1 over n to the nth power when n goes to infinity, that's actually in the textbook. I mean, you can definitely find there to see the limit. But if you're talking about how do I get from this step to here, that's algebra. So do you know that? How I get from there to?
Yeah, that makes sense. What I did is I pulled the absolute value of x out in front of the limit.
Mm-hmm. Oh, sure, you can do that. Yes, you can.
And then I did limit from n to infinity of n over n plus 1 to the n.
Yeah.
And then I took the log of that and took the n out.
Oh, I see. Yeah, you can definitely also do that, but it's just, yeah. I mean,
it's more work and easier to confuse myself, I guess.
Yeah, it's probably because you have more variables in the fraction, so that's definitely going to work harder. Yeah, but it's definitely going to produce the same answer if you. That's the right method, but it's probably more complicated because in this form actually. So
thank you.
One thing you have to familiarize yourself is once you see this expression, you should be alerting yourself that okay, this is going to be related to the e in this fashion, because this is the expression that you should definitely keep in mind, this following one. Okay. So this is the first question that Brian asked. And the second one is similar. So let me let an equals to 2x to the n plus 1 over 8n plus 1 times n to the 8. So an plus 1 now equals to 2 times x to the n plus 2. Be careful. And you have 8n plus 2 times n plus 1 to the 8th power. Okay. Then when you look at the ratio here, when you look at an plus 1 over an, and taking absolute value of that, and what you should be getting here is going to be, let me just write down the answer here without too much detail, because you can definitely work it out. I think it's 8, and you have n plus 1 here. Oh, sorry. Let me write it over here. So an plus 1 over an, taking absolute value, is again something that's similar to what we just did, but it's going to be x over, I think it's 8 times n to the 8th power over n plus 1 to the 8th power. Okay. And this is what you should be getting after you do the correct algebra. Okay, this expression here. Okay. And once we have that, then the question is, what's the limit of these? And it should be easy, right? I mean, you see that when n goes to infinity, this is just polynomial terms dividing each other. This is a polynomial of n of degree 8. This is a polynomial of n of degree 8. And in that case, the limit when n goes to infinity is the ratio of their leading coefficients. Does that make sense? And we know that in this case, the leading coefficients are both 1. So this is actually equals to x over 8 is a limit. So limit when n goes to infinity, this is actually x over 8, and you want that to be smaller than 1. So the radius convergence in this case is 8. Whereas in the previous case is e. That's a radius convergence.
Very straightforward. Thank you.
Yep. And to test on the boundary, you can see that if you test on the boundary, I believe in both cases, in this case, in the second question, if you look at the example here, this should be a closed interval here on both ends, because on both ends it's going to be a p-series. I mean, on this left end, this is alternating series, so it's convergent there. But on this side is a p-series test. Okay, you can see that they are converging there. Whereas in this case, I think it's actually not very easy to see directly what's the interval looks like. So let me write down minus EE. Yeah, I think this is going to be both closed, actually, both open in this case, actually. Right, you can see from here, if x equals to e, then these two would cancel each other, and you have n factorial terms. So this is, both of this is coming from the divergence test. Try it. I mean, this is very important example. I mean, see if you can work it out, actually.
Why would e to the n over n to the n cancel?
Oh, sorry. It's not canceling. I shouldn't be saying it's canceling. It's actually, you're right. No. I think, yeah. No. This is wrong. I was thinking this is E also. So that's why I was making the harsh conclusion there. Thanks, actually, for reminding me that. So this is n to the n. This is E to the n. I think if from what we just did, I believe, actually, I would want to make a jump conclusion actually here to see it's actually both closed. I feel it's both the both endpoint are included in the interval, but it's not quite easy to see actually. So if this is E, then that would give me when n is very large. And actually, I don't know yet. So actually, I will just leave this to you guys. But I have a feeling that, yeah, this has nothing to do with how I feel about these questions. But I think it's both open. But I will check that and send you guys a link answer afterwards.
Thank you.
So this is something I don't know actually. Yeah, on top of my head, I couldn't have a very direct answer to this. Okay. If you know the answer also, you can definitely email me and help me with this too. N factorial. Do you guys know something called Worley's formula? It's actually a very fun one. So I think this is really related to that. Let me Google and write it down for you guys. Or maybe Stirling's formula in a different disguise. Let me find Stirling's formula. Okay, so this is what Stirling's formula is saying. This is actually a very cool fact. And if you want to go further into mathematics, and you should know it, is a given one, is that n factorial almost looks like square root of 2 pi n times n over e to the nth power. Okay, Isn't that beautiful that you have something like this? That n factorial, you have an explicit approximation that this is almost like a square root of n with some constant here, times n to the nth power, and the times, let me get my lamp here. Can you see clear that's what I'm writing here? Can you guys see that? This is what I'm writing. It's square root of 2 pi n, bracket n to the nth power over e to the nth power. If you keep that in mind, you will see that this expression is almost like, with that expression, is almost like a square root of 2 pi n times n to the n over e to the n times x to the n over n to the n. And these two cancel each other, and you're left with x to the n over e to the n and times square root of 2 pi n. You see that? So when x is e or minus e, this term will blow up to infinity no matter what, when n goes to infinity. So I guess from here, you see that this is actually open bracket for both ends. So it's not a question mark, actually it's open, but it's not very easy to see directly. Do you guys follow me now, actually? That is, this is actually following from this cool formula called Stirling's formula. Does this answer your question, Brian? Hopefully, I mean.
Really great, yeah. What was the work that you did there? You did just a little bit of algebra. I guess you cross out the n by n and then see that it blows up. Thank you so much.
Yeah, so by Stirling's formula, I know that how large n factorial roughly looks like in terms of the right-hand side, where it contains n to the nth power, e to the nth power, and the square root of n. So the n to the nth power divides over the denominator, and you're left with x to the nth power over e to the nth power times these. Now, if you plug in x equals to e or minus e, this would cancel out essentially, right? And you're left with 2 pi n squared of that, and that goes to infinity no matter what the sign. So this is going to be a divergence test on that, in that sense.
Thank you so much.
Yeah. But this is actually what Newton already knew like 200 or 300 years ago. That's quite fascinating, actually. This actually has a very deep numbers theoretical relation, and also in terms of what I'm doing in terms of my research topic, this has a different interpretation in terms of spectral geometry. Actually, it's also very interesting too. So yeah. Okay. So any other questions before I move on to the Taylor remainder formula? Any concept you want me to go over, or you're not quite clear? Okay. So if that's the case, let me actually remind you guys what is the remainder formula, Taylor remainder formula. So in Taylor remainder, formula, we have the following expression, is that we have the following expression is r to the n. Actually, let me write down something which is independent. Is r to the n is the max value. Smaller than a, and m. Let me write this out. Actually, this is f to the n plus 1 x value divided by times a to the n plus 1 over n plus 1 factorial. Okay. So this is the formula I want you guys to keep in mind, is that in order to compute, so before I do anything, let me explain what this ARN really means. So remember that whenever you have given a function fx, so given a function fx, right? We know how to write down the first, the nPn, the Taylor polynomial. We can find Pnx, right? We can find the Taylor polynomial of degree n, which is the best nth degree polynomial approximation to your given function, right? Which is given by the f0 plus f0 1 over 1 factorial x plus f square, f to the second derivative over 2 factorial x to the second power, up until f to the nth derivative at 0 over n factorial x to the n, right? This is the best nth degree polynomial approximation to any given function fx, right? It's totally related to the property of fx, which is govern the coefficients of your polynomial, okay? Which makes sense. And if you keep writing this, you have a Taylor series, which is an infinite series, right? A power series in some sense. And the power series has the following, let's see that A is a small number that's contained in the domain of convergence of, okay, so let's see that A is maybe minus A and A is contained in the domain of the summation n goes from 0 to infinity, f to the nth power 0 over n factorial x to the nth power, which is a power series. And then we have that the Pn minus fx, then Pmx minus fx, the maximal value of these in between minus A and A is bounded by Rn. That's the error estimate. Okay. This is where I'm talking about Rn. Okay. So in a pictorial fashion to explain this is that, let me actually do a P2 example here. Suppose you have a function, maybe something looks like this, okay? If I'm interested in the Taylor polynomial approximation to this function, locally, the P2 you computed will be a quadratic, right? It will be some kind of parabola approximation to it, right? This is P2, this is your fx, right? And let's see, this is minus A, this is A. Then what this Rn is telling you what maximally the difference between this function could be is between maybe something like this. So this difference, this discrepancy maybe is given by R2 here. Okay, so that's roughly the pictorial way to understand this. Keep in mind that Rn is just a number. It's a number that's valid for any x value in between minus A to A. And that's what this means, okay? So let's see a couple of examples, how this can be applied to find something. So let's estimate. Let me see if what I'm writing here, you can read it. Okay, perfect. Let's see this. Fx is cosine x. This is something that we know very well, actually. The graph of cosine x, the property of cosine x, we know a lot, right? I mean, all through the semester. So what is the P2 of this function here, right? It's given by f0 plus f prime 0 over 1 factorial x plus f second derivative 0 at 2 factorial x squared, right? This is what we get. But if we calculate more explicitly, what is f0 is 1, right? What is f prime 0 is sine x of 0 is 0, so this term doesn't exist. And for cosine x, you have minus, something like this. Okay, so the P2 of this function is given by 1 minus x squared over 2. My question is, we want to estimate cosine 0.6. Let's see, we want to do something like this. Okay, if we want to estimate what is the value of cosine 0.6 degree, how can we do that? We need to know the difference, right? We want to estimate the error of this by using P2.6. Okay. So we know that this is a good approximation. P2x is a good approximation of cosine x. That would mean that P2.6 degree almost approximate cosine 0.6, right? This is something we know from the very definition of the Taylor polynomial as the best approximation polynomial, degree polynomial of fx. So we know this value of this polynomial approximates the original function very closely. But how closely are they related? That's a question. What's the error? Can we estimate the error? And that's the thing. So in this case, we know that the error by using this to approximate this part is given by R2, right? Is given by R2 in our previous notation, is actually given by the maximum value of x smaller than 0.6 of which derivative are we using to do the approximation if we use P2? It's always 1 degree further, so we are computing the third derivative of fx and times the length, which is 0.6 to the third power over 3 factorial. Okay, so this is the R2 we are using. So we know the error is going to be smaller equals to R2, which is computed by this expression here that I just wrote down. And what is that? So what's the third derivative of cosine? So cosine x, first derivative is sine x, and second derivative is minus cosine x, right? The third derivative is sine x. So roughly speaking, this is not roughly speaking, but it's actually sine x absolute value, taking absolute value between 0.6 to this, okay? And to the 0.6 to the third power over 3 factorial. Here's my question. To our disappointment, we have to estimate the maximum value of this function sine x in between negative 0.6 to 0.6. What's the maximum value of this expression that can be? Anyone who knows?
There's 1.
1, exactly. We don't have to really find out sine 0.6. That's the point, because we can just use 1 to make it slightly larger. Okay, so this is smaller than 1 times 0.6 to the third power divided by 6, which actually equals to 0.036. Okay, so you see how many times we have actually enlarged the error, the upper bound. We don't know exactly if the error equals to R2, but we know that the error is going to be smaller than R2. That's something we know. But to compute R2, we don't know how exactly this value is, but we actually enlarge the value a little bit so that this is actually bounded by 1. And even using that, we see that the error is pretty small. It's 0.036. It's very small. So that means this approximation, by plugging 0.6 into this polynomial, the value you computed actually is very good approximation to cosine 0.6 degree already. And that's actually a good news, right? I mean, without calculus, without Newton's contribution, we don't know how to do this very effectively, right? And we don't know if we can find a good approximation there. But with all the tools we have learned in this semester, suppose you are an engineer in the future, if someone asks you to do an approximation, what you can do is you can always first find the best nth degree polynomial approximation to that and use that value to give an estimate. Not only you can estimate the value, you can also find out the upper bound for the error you actually get by using the remainder formula. That's the whole point of this formula here. Okay.
Oh, I have a quick question.
Sure.
I guess I'm a little confused about the Taylor polynomials and which P correlates with which with how many terms. So P2 is the I thought for cosine would just be 1 because the second term is 0.
Oh, and it's not the second term. It's actually the second degree polynomial.
Okay.
The 2 here indicates that you are looking at a polynomial of degree at most 2. So what is the degree? So this is degree 0 term. You should see that.
Yeah. 0, 1, and 2.
1 degree. And this is degree 2. So that's how I get this, because you can see this is x squared term. So that's why even though this term is 0, you're right, but the second term is 0, but the degree term is still there.
So P3 would be the same as P2 because there is no P. There's no third degree.
Exactly.
Got it. Okay. Thank you.
Perfect.
Appreciate it.
And this is the way actually to how do you find Pn? Actually, this gives you you see how I can keep going, let the n goes larger and larger, and that forms a power series, right?
Right.
And one thing that we didn't emphasize enough is that when n goes to infinity, you get power series, but that power series may not converge to cosine x. It's possible, but in the very fundamental examples we have learned, e to the x, cosine x, sine x, for these kind of class functions, the power series you produce by continue like these actually converges to cosine x, sine x, and e to the x. These functions equal to each other. Remember, like two discussions before, you asked me the question that e to the x equals to 1 plus 1 over 1, x over 1 plus x squared over 2 factorial, things like this. Why they are equal? Right. We actually prove that. They are not automatically equal to each other. You actually have to prove it.
Thank you. Yeah.
And that's another application of the remainder formula estimate, actually. We can use the remainder estimate to see that if the power series difference, if the Pn compared to fx is actually getting smaller and smaller, that means the power series we get actually is going to converge to fx. And that's another way to see this application of this remainder formula estimate. Let me actually write down what I just said, actually. So remember this. We know that we have e to the x, right? If we compute the Pn of e to the x, we get 1 plus x squared over 2 factorial up until x to the nth power over n factorial, right? If we're just doing the Taylor polynomial approximation, we get this polynomial. If we let n goes to infinity, we get the following series, right? So let me call this function another function gx, and this is fx, and this is Pnx. So what's the relation between these three things? We start with a given function fx. We can always compute this Taylor polynomial, the best nth degree approximation. This is the approximation. So this is the approximation polynomial. We can always compute the approximation polynomial out of fx, right? If we keep computing more and more terms, we get the power series, which is gx. And for gx, it may have a radius of convergence. Let's call that minus r to r, okay? So in some sense, this is the domain. So this is the interval convergence, or slash, this is the domain of the function, right? As a function. You should really think about this as a domain of this given function here, okay? Then the question is, what's the relation between gx and fx? In this case, in the previous lecture discussion, I already told you they are actually equal to each other. So today, we are going to try to use the remainder estimate to prove that they actually are equal to each other in a different way. So first of all, what's the relation between this and this? This is the truncation partial sum of gx. Do you agree? The Pnx is nothing but the partial sum of gx, this power series. So to argue that gx actually equals to fx, all we have to argue is fx minus Pnx goes to 0 no matter for which value x you take. So we have to estimate what's the difference between these two functions, right? That makes sense? Any question at this step? So to estimate this difference here, we know that by the remainder estimate, this is smaller than Rn. And also we know that in this case, the radius convergence actually is from negative infinity to positive infinity. So there's nothing here actually. So what is Rn? Rn is the maximum value of x smaller than infinity, actually any x, basically meaning any x, e to the n, the e to the x to the e to the x actually, right, with absolute value. And taking x to the n plus 1 over n plus 1 factorial. Okay. So this is the maximum value of that. And my question is, given any x, what's the limit of this as n goes to infinity?
Oh, why do you have e to the x and x to the n plus 1 in the numerator?
X to the n, x absolute value to the n plus 1 is nothing just from the remainder estimate. You see that? You have this a here, right?
I'm just not sure why you have e to the x up there as well.
E to the x is the f to the n plus 1's derivative.
Gotcha, thank you.
What happens when you differentiate e to the x n plus 1 time? You still get e to the x, but I'm taking the max value of these, so that's why I take the absolute value of these here, roughly speaking. Yeah, so I should just omit this part actually. Okay. So my question here is really let's just pretend x is fixed number. It's just some a here. Let me just call this a. Okay. You have e to the a, which is fixed, a to the n plus 1 derivative, which grows like n plus 1 polynomial of a, but in the denominator is what? It's n plus 1 factorial. It's growing really fast. So that's why this always goes to 0. That makes sense? So that means the remainder estimate, the remainder term, for any x will eventually goes to 0 if n is large enough. That means this difference here is always going to be converging to 0, going to 0, right? That means the nth partial sum, the nth Taylor polynomial, subtract fx is sufficiently small when n is sufficiently large, meaning they converge to each other. That makes sense? So that's a different proof that e to the x actually equal to j to the x. But let me emphasize again, this doesn't happen always. It's only for very specific, very special functions that the power series, the Taylor power series you produce actually equal to fx. There are plenty of examples where this is not true. Okay, so this is something that's the subtlety behind the whole Taylor remainder estimate and the whole power series thing, which we won't be able to discuss in this semester. And that's something you have to really go to maybe, I think that's all-nerd analysis, something like 400 level mathematics to learn about this kind of difference. Okay, but at this moment, that's all I can see about this whole picture is that given any function, you can compute the polynomial. From there, you can get the power series. And if you're lucky, they are equal to each other. And their difference will be estimated by the remainder estimate, which is given by the formula I wrote before. Okay, so that's everything you need to know for this semester before the exam, actually. Okay, so has Dr. Chadwick mentioned that the polar coordinate will be on the exam or not? It will not. Okay, perfect. So we don't have to worry about the polar coordinate. So from today, I want you guys actually to really look into the previous exams in the test bank and try to, start your review. I mean, this is going to be the next 10 days is going to be your opportunity to really review, right? I mean, before the exam. And so the fourth exam will be on Friday, and the final exam will be on next week, I think. That's correct. And any other questions about the concepts we have learned so far in this exam, in this semester? that you are not quite clear, you can always ask me now. You can send me email, and I will review next week, actually, if that's possible. Okay. I guess there's no question for the day. If that's the case, I will just let you guys go and enjoy your lunch, and stay safe, and email me whenever you have questions, and good luck on Friday.
Thank you, Bo. Do we have discussion next week?
I think so. Otherwise, I will just do it myself, I guess, for you guys too, as a review before the exam. Right.
Thank you so much.
Yeah, no problem. I mean, this is a very special time. I think that you guys definitely need some more, review to get ready. And to be honest, I don't even know what the final exam will be actually on my own. I will have to discuss with Dr. Chadwick also to find it out also. Yeah. Any other questions?
Really appreciate you, Bo. So we'll see you Tuesday then.
Yeah, for sure.
Thank you so much.
No problem.
Well, thank you, Bo.
Yep, thanks. Okay. So see you guys.